I now call upon Dr. Kate Mays to present our second nominee for the honorary degree of Doctor of Science.
Thank you, Mr. President. Our second honoree, Dr. Stephen G. Brush, is an internationally renowned expert in the history of science and science education. He has spent his career as a professor, researcher, and author of more than 300 works. His most recent book, entitled Making 20th Century Science: How Theories Become Knowledge, has recently been published and represents 20 years of studying historical scientific theories proposed by scientists and the means by which they develop relevant predictions of scientific results and how these findings make their way into scientific knowledge. At age 14, Professor Brush, who was in high school and at that time excelled in both science and debate, entered the Westinghouse Science Talent Search and was chosen as one of 40 finalists. At that time, Professor Brush's father thought that maybe his son might amount to something. So instead of Stephen going to his local university, the University of Maine, his father made calls to Harvard, MIT, Yale, and Princeton to see if his son may make their enrollment. Even though it was past the time for enrollment and those deadlines, Stephen was accepted at Harvard, MIT, and Yale. So at age 15, he enrolled as a chemistry major at Harvard, but because his professor of physics was more interesting, he changed his major to physics and graduated in 1955. He then became a Rhodes Scholar and continued his studies at Oxford, completing his doctorate in theoretical physics in 1958. After this, Professor Brush worked at the Lawrence Radiation Laboratory in California, researching properties of matter at high pressure, which became important in the future study of stellar and planetary structure. In 1968, Stephen joined the faculty of the University of Maryland, where he taught at the Institute for Physical Science and Technology. He became the university's first full-time historian of science and later became a distinguished professor of history of science in 1995. Besides his recent book, he has written extensively on the history of science. Another book, The Kind of Motion We Call Heat, A History of the Kinetic Theory of Gases in the 19th Century, received the prestigious Pfizer Award from the History of Science Society. So you see, Stephen proved his father right. He did amount to something. Professor Brush has had a very productive and illustrious career in both history and the sciences. He has two children who are both here today, and we welcome them, and also two granddaughters. One of them, Jennifer Roberts, is among our graduates today, receiving her physics degree from USciences. Needless to say, her grandfather is very proud of Jennifer, and I am equally proud to present to you, Mr. President, our second distinguished honoree for the Doctor of Science degree, Dr. Stephen Brush.
On the recommendation of the nominating committee and with the approval of the Board of Trustees, and by virtue of the authority granted this institution and vested in me by the Commonwealth of Pennsylvania, I confer on you, Stephen G. Brush, the degree of Doctor of Science, honoris causa, with all the rights, privileges pertaining thereto, in testimony thereof. I ask that you be vested in the hood symbolic of the degree and present you with the official diploma. Please join me in congratulating our honorary degree recipient. Congratulations. It's wonderful. Thank you.
Thank you. I have a different metaphor for my subject. As we were driving north on Interstate 95 this morning, when we entered the state of Pennsylvania, we were informed by a very large board, Pennsylvania is the state of independence. And about 5 seconds later, we were also notified by another billboard on the other side of the road, you better click your seatbelt shut or you will be fined if you don't buckle it. So this is a good example, I think, which many of you perhaps have seen these signs, that in studying the question of what is science like, how do you do science, how do you become successful in science, you have to recognize that there are some very loose rules about how you go about doing it, but at the same time, there are some ways of doing science that seem to be more acceptable than others at any given time. In many of your courses and textbooks on science, you were told that the scientific method is to formulate a theory, make a prediction of a previously unknown fact, then test your prediction by doing an experiment. If the prediction is refuted, it doesn't come out the way you thought it would, you must abandon or seriously revise the theory. According to this view, giving a new explanation of already known facts is useful but not so impressive as a successful prediction. In my recent book, which I am donating a copy to your library so you'll have a chance to read it, Making 20th Century Science, I looked at this question of which is more successful in getting your theory accepted. Is it making a successful prediction, which is then confirmed, or is it giving a good explanation of facts that were already known but didn't fit together in any coherent theory? And my conclusion was in looking at a number of cases of well-known theories that you could do either. There are examples of successful predictions, there are examples of successful explanations, but the most important theory, in my opinion, in 20th century physical science was quantum mechanics. And quantum mechanics, which I hope you are all familiar with as graduates of this university, was generally adopted by all the experts in atomic physics simply because it gave a better explanation of the facts about how atoms behave than any other theory. In fact, there were many theories of how atoms behaved before 1925, but they each would only explain some part of the mystery. They weren't consistent with each other. There was no coherent single theory. Quantum mechanics, when it was proposed by Heisenberg and especially by Schrödinger in the form that is usually used, was accepted almost instantly. By instantly, I mean that the theories of Heisenberg and Schrödinger came out in 1925, and by 1927, they were generally accepted by all the experts in atomic physics. And this was before there was any prediction that had been actually confirmed. There were lots of predictions later, but in less than 2 years, the theory was accepted before there was any time to make any of the tests of the predictions. So, therefore, in the cover of my book, I show Schrödinger as the person who is a counter to the usual doctrine that you have to make a prediction in order to have your theory accepted. The theory has to make successful predictions. And you can look in the program of today's exercise. On page 19, you will see that the University of the Sciences offers two scholarships or prizes called the Norman Ramsey Commencement Research Award, and they are presented to a student who has demonstrated outstanding performance in all aspects of the subject, but in particular that a graduate doing hypothesis-driven research in the biological sciences or in other sciences. There's two of these awards. In other words, that's what is still taken as the way you should be doing physics. You should propose a hypothesis and then try to prove it or disprove it. So at this very university, prizes are given for hypothesis-driven scientific research. Now, I want to tell you about one case which was a case where events in the world outside of science saved a scientist from having his theory refuted by experiment, and that was because he had, in fact, made a prediction which turned out to be wrong, having to revise the theory to explain the experimental result. Now, what happened was that, let's get the appropriate place here, in his early theory of relativity, Albert Einstein predicted that starlight passing near the sun would be deflected by the sun's gravitational attraction. This was just about 100 years ago. He persuaded a team of German astronomers to test this prediction. His prediction was that the deflection of starlight by the sun's gravitational force would be 0.87 seconds of arc. And it was known that the best way to test this prediction was during an eclipse, a total eclipse of the sun, which would take place on August 21st, 1914, and which could best be observed from the Crimea Peninsula. That Crimea Peninsula has been in the news recently, so you may appreciate what happened next. On June 28, 1914, the Archduke Francis Ferdinand of Austria-Hungary had been assassinated by a Serbian nationalist, Gavrilo Princip. This was the event that triggered World War I, as we now call it. At the time, it was known as the Great War or the war to end all wars. But we no longer call it that, having seen lots of other wars. World War I was triggered by this assassination. Germany declared war on Russia on August 1st, 1914. So Einstein had persuaded a group of astronomers, German astronomers, to go to observe this eclipse and test his theory. However, when they arrived at Crimea, which, as you know, is near to Russia, they were arrested as enemy aliens by Russian soldiers and prevented from making their observations. They eventually got back home, but they had missed the opportunity to actually test Einstein's theory. Subsequently, Einstein revised his theory and discovered that, in fact, the deflection ought to be twice as much as he had originally calculated, because this was when he took into account some other important effects. So if, in fact, Gavrilo Princip had missed his opportunity, which he might well have, then they would have made the observation, the astronomers would have made the observation, they would have shown that Einstein's prediction was wrong by a factor of 2. However, they were prevented from making the observation, so nobody knew this at the time, and later Einstein revised his theory and found that, in fact, the prediction should be twice as much as he had originally calculated. And then later, after the end of World War I, the observation was done by British astronomers who confirmed Einstein, and this was generally regarded as a great achievement in science, which the London newspaper proclaimed as being overthrowing. The Times of London said this was a revolution of science that was started by Einstein's theory as confirmed by a British astronomer led by Eddington. This was in 1919, just after the end of the war. The Times of London said this was one of the greatest achievements in human thought. And those of you who were reading Time magazine back in the 20th century, just before the beginning of the present century, may recall that Time magazine, which in those days would always feature the Man of the Year, and at some point they started allowing women to be the most important person in the year. But Time magazine, having started the tradition of having a Man of the Year every year, named Einstein Person of the Century. So in the popular mind, as shown by Time magazine, Einstein's work, which of course had become also famous through the development of the atomic bomb and transformation of mass into energy, this was now leading to the general opinion, as expressed by Time magazine, that Einstein was the most important person in any field in the 20th century. And Princip, the assassin, probably had never heard of Einstein, but in fact, his work, his assassination, saved Einstein's reputation as the most famous scientist in the 20th century. I think this is an interesting example of how unexpected things can happen. It's also an interesting example of how you still get more credit for making a successful prediction than by making a good explanation. And certainly this was in the case of Einstein. Just imagine to yourself what would have happened if Princip, the assassin, had missed. Then the German astronomers would have made the measurement and found that Einstein was wrong by a factor of 2. And then Einstein would have to be in the embarrassing position of saying, oops, I missed a factor of 2. The real result should be this, and basically giving an explanation of why the actual result was not what he had predicted. So this is, I think, just one example of the many fascinating things in the history of science which you can learn, and then you can think, well, why should the making of predictions be the be-all and end-all of science? And even in the biological, social sciences, the tradition is also carried on. I understand there are some journals in psychology, for example, that won't even accept a paper unless you make a prediction and try to test it. So that's become known as the scientific method, yet doesn't always work that way. Thank you.